All right. I have made the announcement in Gather, so I think we're ready to get going. Um, can everybody hear me?
We can hear you.
Yes. Excellent. And I hear you too, so that's excellent. Okay. Um, I'm very pleased to present Emina Torlak for our keynote presentation of the day. Emina is a senior principal applied scientist at AWS. She even puts this on her slide right in front of me, so it's super easy to remember all these details. And until last year, she was also an associate professor at the University of Washington, with which she retains an affiliation. She's well known for CodeCode, which is a widely used constraint solver, which is super fun, has a nice API. For Rosette, which is an embedded DSL in Racket for building SMT solver assisted programming languages, which allows you to do all sorts of really nice verification and synthesis tasks quite easily. It's really a lot of fun. And more recently, which is what she's going to be talking about today, Cedar, which is a security policy language which has been formally specified and verified in Lean. And so she'll be talking about using Lean in industry for money, which I think is an excellent thing. I'll turn it over to you. Thank you.
Thank you so much for that great introduction, and thank you all for being here. It's my pleasure to join Lean together and talk about Cedar, which is a new language for writing authorization policy that is expressive, fast, safe, and analyzable. We'll start by talking about what authorization is, why you would like to have a language for it, and why and how we build Cedar using formal methods and Lean in particular. So authorization is the problem of determining who can do what in a multi-user application. Every multi-user application that you're using today has to solve this problem. So everything from social media to document sharing to online banking. If there's more than one user, they have to be able to determine whether a user is allowed to perform a specific action to a specific resource that is important to the application. In principle, authorization is a solved problem. They're well-known access control models that you can use within your application. For example, you can give access to your users based on their role within an organization. This is called role-based access control. You can give them access based on the attributes of the users or the resources. For example, the user zip code, and this would be attribute-based access control. Or you can give user-based access based on relations to other users or to the resources. So perhaps I have editing access to a document if I'm designated as an editor of that document. So the theory is well known, but implementing one of these models inside of your implementation is still very hard to do today. In particular, it's hard to initially develop the authorization code. It's hard to audit it, to convince somebody that you're giving the right access to the right people. And it's hard to maintain it, to change the code and evolve it as you go along. To see why, let's consider a toy multi-user application, which we're going to call Tiny To Do. And Tiny To Do allows users and teams to create, manage, and share to-do lists, okay? So it's like photo sharing, except that we're sharing and managing to-do lists. Normally, when people write applications like this, they will embed the authorization logic directly in the code. So what you're seeing here in the slide is a Python-like piece of code that is implementing the get list action for Tiny To Do. Okay, so if you imagine having a UX and you're trying to do something with the lists, well, one of the things that you want to do is to actually get the list displayed on the screen. Can you perform this action or not? Well, this get list procedure is trying to determine that. So it has a bunch of nested conditionals that perform the authorization logic, and then it does, and if that passes, it performs the action that it's supposed to do. Now, it's pretty easy to see that doing this inside of the code is tricky. If you stare at this code long enough, and you'll be staring at it while I've been talking, you will realize that what this thing is trying to do is to give access to a list if the principal, so the person trying to access is an administrator or the owner of the list, or an editor or the reader of the list. Now, I said all of this positively, but the code is actually implementing the negation of this, which is super tricky. And it's actually these kinds of mistakes, getting these negations and the nesting wrong is 4 out of the 25 top security vulnerabilities that people have made in 2023. Of course, it's also hard to read this code and convince somebody that is doing the right thing. If you want to change the code or read it, you have to understand the whole application. You have to recompile the whole implementation application and redistribute it. So this is where authorization languages come in. The basic idea is to separate your application logic from the authorization logic. And you write the authorization logic as policies in a dedicated domain-specific language, an authorization language like Cedar. You don't have to be a Cedar expert to quickly glance at these policies and convince yourself that they are doing what that complicated logic was doing before, okay? So it's giving access to a resource if the principal is the owner to a resource, if the principal is an admin or an editor or a reader of that resource. The thing that's nice about this approach is that your actual application code never changes if you need to change the policies. They're completely separate. All you need to do within your application is make a call to the authorization engine for your language, which will evaluate these policies with respect to the request and determine whether the policies allow the request or not. So this is much easier to author, audit, and maintain. Cedar is a new authorization language that is already used at scale within Amazon. It powers two services, Amazon Verified Permissions and Amazon AWS Verified Access. And you can find out more about it. You can download it. You can play with it at the website. So Cedar is open source. It comes with batteries included. First is an ergonomic syntax and semantics, which we're going to see in detail a bit later. The second is fast and safe runtime, and I'll tell you in detail what I mean by that. And finally, a suite of powerful static analysis tools that let user write correct and safe policies. We have built Cedar to a high standard of assurance using a development methodology that we call verification guided development, which uses mechanized reasoning with lean and differential random testing. Now, before we dive into the details of why and how we built Cedar, let's talk about why we did it. What's challenging about building an authorization language and why we took on that challenge? The main problem is that even though it looks like a simple problem, there's a hard set of trade-offs that you have to manage. You basically have to satisfy four competing concerns. Your language has to be expressive enough to capture all of the use cases that we've seen before, like role-based access control, attributes-based access control, relation-based access control. It has to be safe, so you have to provide people tools so they can write policies without having mistakes like type errors cause their policies to fail at runtime, at evaluation time. It has to be fast in applications such as Zero Trust, where you're making millions of calls to your authorizer in order to check every single access. Authorization has to be super fast. And finally, we want authorization policies to be analyzable, meaning tools should be able to reason about the semantics of these policies fully automatically and consider deep semantic properties of these policies, like, is this policy ever going to give public access to a resource that should always be private? Now, we built Cedar because we look at the space of existing solutions, and we didn't find anything that satisfied all four of these constraints. There are existing authorization languages that are very expressive, but they are not as performant as we would like, and they're not analyzable. On the other end of the spectrum, there are authorization languages that are highly performant and that would be analyzable, but they're not expressive enough. So for example, they can express relation-based and role-based access control, but not attribute-based access control. So we built Cedar to balance all these four of those all of these concerns. It's a new point in the design space. In the rest of this talk, I'm going to talk about how we did it, how we actually designed and built Cedar, starting with the syntax and the semantics of the language. So let's start with the simple thing, which is the syntax. Every Cedar policy consists of three parts. The first one is the effect of the policy, which is either to permit or forbid access. So I'm giving you explicit access or I'm explicitly removing access. The second part is the scope, which optionally constrains the principal, action, and resource using either equality or the in operator. And we'll talk about the in operator a little bit later on, but think of it as testing group membership. So scope is very syntactically constrained. You can only do two things in it, and we'll see why. And finally, optionally, If scope is not expressive enough to say what you need to say, you can write conditions which are prefixed by when or unless, and unless is negation of when. These conditions are Boolean expressions, which are usually over the attributes of the principal, action, or the resource. Policies operate over 4 variables. So you've already seen 3 of them: principal, action, resource. The 4th one is context. We haven't mentioned it yet, but think of it as a record which stores transient information about the request, things that are not stored in a database, like current time or source IP and things like that. We populate these 4 variables from the request that is passed in by the application, which is trying to determine whether access is allowed. And a request is allowed by a set of policy if it satisfies at least one permit. So all the Boolean conditions evaluated in the right way to satisfy permit policy, and no forbid policies. Okay, that is the only condition under which a request is allowed. So let's see a concrete example. Suppose that we have just one policy in our entire system. So this entire policy store, there's just one policy. It's the policy on the slide. And we want to evaluate it with respect to this particular request and the entities and the attributes for those entities, which are shown on the slide, the things that we have been seeing before. So is Kesha allowed to perform the get list action on list 1, 2, 3? Well, the answer is yes, because if you look at the hierarchy, Kesha is a member of the temp team, and members of the temp team are in the readers group for this list, and principals who are readers are allowed to access it. Okay, so far so good. She's allowed to see it. How about this other user, Emma? Well, Emma is not in the temp group or actually in any editor or reader group for this list. And there is no other policy that will allow her access, okay? So the answer is no. This property is important for authorization systems. It's called default deny, meaning if there is no explicit permission to do something, the answer is no. In order to give Emma access, we have to add another policy, which is the policy that you've seen before. And this policy says that members of the administrator team can perform any action they want, not just get list, on the resources that I need to do application. And Emma, in this case, gains access because she is an admin. Okay, so the data model syntax and semantics for Cedar were carefully designed to allow, to support these 3 common access control models: role-based access control, attributes-based access control, and by combining the 2, relation-based access control. So let's see how we support RBAC first. What you see on the slide is this policy that we've seen a couple of times already, which lets principals who are member of the admin team do anything they want in this application. This is an instance of a role-based access control policies because we're giving permission to the principal based on their membership in an organization or the membership in a group. In general, this idea of an entity is a core concept in Cedar. Think of entities as stored objects in a database, which have identity. And they can, and we use entities to represent principles and actions and resources. Entities are organized in a directed acyclic graph, a DAG, which represents whatever hierarchy you want to represent with it. So, with people, it's going to be something like, teams and departments and so on. And with resources, it could be folders and, depending on exactly what you're trying to model. But essentially, that's the main idea. You have these entities and you can put them in this graph to express hierarchy and grouping relationships among them. You navigate the entity hierarchy using this in operator, which represents transitive reachability. So in this case, if you look at the example on this slide, Aaron is a member of the temp group, even though he's not a direct member of that group, he's a transitive member of that group. So the constraint Aaron in team temp would always be true. Now, if you think about the behavior of this in operator, you will very quickly realize that this operator, at least on the surface of it, on the face of it, sounds like a bad idea, right? Testing transitive reachability in a graph at runtime would be a very expensive operation, and we want these authorization requests to be fast. So how do we actually do it? Well, it turns out that we can perform this check in constant time. And the trick is that we define the semantics of Cedar, and of course we implement it that way too, by having it operate not on this DAG directly, but on the transitive closure of the DAG given as a map from entities to their ancestors. This means that the application, which is using Cedar, has the option of maintaining incrementally this transitive closure of this graph in their database. So whenever they need to Cedar to answer a request for them, they give us the subset of the map that's relevant to that request. So the actual runtime is going to be super fast. It's going to be constant time as opposed to linear search over a potentially massive graph with thousands or even millions of entities. Okay, so if RBAC is not enough for your application and you actually need to refine access by providing conditions that rely on the attributes of the principal on the access, then you will add a condition to your policy. Every entity, in addition to being a member of this hierarchy, optionally having some parents, also has a record associated with it, which is a binding from strings to Cedar values, and the strings represent the attributes. Cedar value can be one of three things. It can be a primitive, so an atomic value, a Boolean, int, string, or an entity. It can be a set of values or a record of values. So it has this nested structure. So you can have a set of sets of records of sets in Cedar. And this is an important point, which we'll come back to later when we talk about the formalization. So just file it away from now. Whatever you can express in JSON effectively, and this is intentional, you can encode it as a Cedar value. And JSON is a good choice here because this is the common format that people use to represent the data that's used for authorization. The expressions in this expression language are pure, meaning there are no side effects and they're free of loops. The set of operators that you're allowed to use in order to operate on these Cedar values is limited. It is carefully chosen to ensure that nearly all Cedar policies are going to terminate, well, they're always going to terminate, but they're going to terminate fast, so in linear time, and the worst case performance is quadratic. Another reason why we chose these operators carefully, as we will see later on, is that we wanted to make sure that the Cedar language is reducible to satisfiability modular theory formulas that are decidable, and the reduction has to be sound and complete so that any analysis that is based on this reduction gives you no false positives and no false negatives, okay? So the language is carefully constructed to let you say just enough to express authorization problem while supporting fast evaluation and analysis. Now, you might have noticed that every operator that can go in the scope of a policy can also appear in the condition. So in some sense, scopes are redundant, right? You can't actually write a policy without specifying any scope constraint. And you might be wondering why we bother to make the syntax look this way. Why separate the scope from the condition? Well, there are two reasons. The first one is readability. So here is a hypothetical syntax for Cedar on the right-hand side of the slide, which doesn't use scopes. And you can see that this is much harder to read because you have to visually parse this policy to figure out which constraints are role-based access control and which one are attributes-based access control. With scopes and condition, the separation is clear and it's very easy to audit and scan policies. Another reason is scalability. It turns out that we constructed the syntax carefully so that Cedar policies as a whole have a property called slicing, which improves sound and lean, which lets us evaluate a subset of a huge set of policies and arrive at the same authorization result that we would get if we were to evaluate the entire set. So in real applications of Cedar, some of them have hundreds of thousands of policies, and selecting a small subset of them soundly is necessary for efficient evaluation. And we select that subset through an indexing algorithm, which we call policy slicing algorithm, that is based on this constrained syntax of the scopes, and that lets us do this quickly. So basically, policies that are more readable are also faster and more efficient to execute. So the language syntax nudges you toward writing readable and fast to execute code. Okay, so that's it for the Cedar syntax and semantics. I'm going to briefly tell you about the kind of tools that we provide to let users write correct Cedar policies. And these tools are important because they will make an appearance later in the talk when we talk about the formalization. There are two kinds of tools that we provide today. One of them you can go to GitHub and download and play with. That is the policy validator. It's a type checker. And the other one, which we're going to talk about shortly, is the policy analysis tool, which works by reduction to satisfiability modular theories. But let's talk about the policy validation first. The policy validator takes as input a policy, unsurprisingly, and a schema. So think of the schema as providing type and hierarchy grouping information about your applications, okay? So here on the right-hand side, we're seeing the schema for tiny to-do. And it tells you the signature of each action. So think of actions as methods. And the signature of the get list action is that the principles for the action must be of type user and the resources must be of type list. These actions can be polymorphic, so you can have more than one principle and resource type apply to a given action. The schema also provides the types and the kind of attributes that an entity may have. Okay, so here's the schema for the list in the tiny to-do application. And the schema also tells you how various types of things can be grouped together. So teams can be grouped into other teams and into the application entities, and users can be in teams and the application. Same for the list. But note, for example, that it would be nonsensical to wrap a team into a user. Okay, so that is not that direction in the entity DAG is not allowed by the schema. The validator checks whether the policy conforms to the schema as follows. So here's an example. I'm going to do a quick walkthrough. First, we look at the action. In this case, we see that the resource has to be a list. Because the resource is a list, we know that it has a required attribute. We also support optional attributes, resources and editors. So it is safe to access this attribute without checking whether it exists first, okay? So the type checker knows this. And finally, we can check that this principle in constraint makes sense because resource.editors is a team and it is okay, it makes sense to check whether a user is a member of the team. In addition to type errors, this validator can check all sorts of other errors. And the key ideas behind it, the thing that makes it interesting is that it's flow sensitive. So for example, if you check for a presence of an attribute and then access it, the validator will know that this is a safe access versus if you don't do that. So it actually understands the flow through your policy, and it knows how to deal with these polymorphic actions, which we're not showing you here, because it's a quick introduction. We've modeled this validator, as we'll see later on, in Lean, and we have proven that it sounds, meaning that if validations succeed, your policy is guaranteed not to exhibit any runtime type errors when you evaluate it, as well as any of the other errors that we guard against. Okay, so this is validation, and it gives you a sanity check, kind of a baseline of safety for your policy. But what if you want to ask a deeper question about the semantics, the behavior? What does this policy actually do on all possible inputs? One example of such a question that you might want to ask is, suppose that you want to build a refactoring tool for your policies, okay? You have a set of 10 policies, you want to munch them together and end up with a set of shorter 5 policies. How do you know that these two sets are equivalent on all possible requests, all possible entity hierarchies? We answer that question by running a symbolic compiler. This compiler is a tool that reduces the semantics of a formula to a logical formula in SMT, and it uses an SMT solver to check that the negation of the property that you care about is unsatisfiable. This is the usual trick that we use when we do verification of this kind. The key feature of this reduction is that it produces formula in a decidable fragment of SMT, which if you've done these reductions before, you might find surprising because of that in operator that we have in Cedar, which seems like it would require having transitive closure or quantifiers, both of which are, of course, undecidable. And we are able to avoid that thanks to the careful constraints that we have put on Cedar's design. We are in the process of proving that this algorithm, that this reduction is sound and complete, meaning that it produces no false negatives. If it says that your policy satisfies a property, it really does. And if it says that it doesn't satisfy it, the counterexample that it produces as a witness is a real witness. It is not due to some imprecision in the tool. As a concrete example, consider these two policies and suppose that you want to refactor them into a single policy that does the same thing. Okay, so these two policies give everyone permission to create lists and get the list that they own. And it forbids interns from creating lists. If we ask the analysis whether these two policy sets are equivalent, the answer is going to be no. And the analysis produces a counterexample, which shows an input on which the original policy set allows access. So Aaron, even though he's an intern, is actually allowed to perform this get owned lists action, but the refactor policy doesn't allow this. We can fix the refactor policy by strengthening its condition, and in this case, the analysis is going to conclude that they are the same. Okay, so that is the Cedar design and the tools that we provide for writing safe and correct Cedar policies. And now we're going to talk about how we actually build Cedar using formal methods in general and Lean in particular. We use a process that we call verification guided development. We apply this process to every single core component of Cedar: the authorizer, the evaluator, the validator, the symbolic compiler, the new components that we're building. So each component has to go through this process, which I will describe and demonstrate on the authorizer and the evaluator. But keep in mind, and this becomes important later on, that we actually have to do it for every component of Cedar, the full system, not just the core semantics, but also the tools that operate on the core semantics. So from the point of view of a user, the interacting with Cedar sort of looks like this. You give it a request, your entity data and the policies, and the Cedar authorizer invokes the evaluator, which evaluates each single policy against the requested the entities, and it combines the result into a single authorization decision, allow or deny. The authorizer and the evaluator, in fact, all production components of Cedar are built in Rust. We chose Rust because of its memory safety and performance. Rust is very fast. Cedar takes less than 10 microseconds on a typical authorization request, which is several orders of magnitude faster than existing authorization engine. Now, Rust gives us speed and memory safety. But what about semantic safety? How do we actually know that the code that we wrote in Rust matches the language specification? And what is the language specification? In Cedar, we specify the language formally by writing a reference implementation. Think of it as a tiny, the simplest possible, the most readable implementation of a component that you can imagine, functional code, that you would be happy to give to a user and say, hey, read this tiny piece of code in order to understand how Cedar works if you have deeper questions. So we formalize the language by providing reference implementations for everything. We check that each production component matches its reference using a technique they call differential random testing, which was developed for testing of compilers. The basic idea is that you randomly generate millions and millions and millions of inputs, which you feed to both the reference implementation and the production, and you run them. Remember, reference is executable. It's real code that you can run. You see their outputs and you compare them. If they disagree, you found a bug, and then you go and fix it. If they agree, you generate a piece of evidence that the two are equivalent. And the method that we use for generating these inputs is coverage guided. So it actually tries to cover as much of the Rust code as possible, which gives us a high confidence that the production engine implements the reference implementation. Now, a key part of this development method is that we develop the reference implementation not in Rust itself, but actually in a language that is enabled with a verification tool. So some kind of a verification language. We use the verification language's theorem prover to actually prove all of these important properties of Cedar's design that we have covered throughout this talk. So things like the authorization is default deny overrides allow, that slicing algorithm that we talked about for indexing and selecting policy is sound, and so is the validator, and so is the symbolic compiler, and so on. So basically, every property of the design itself, of those algorithms on whose correctness we depend, we prove it. And we use differential testing then to check that the production matches the reference. This process is labor intensive. There's no way around that, but it is very effective at giving you implementations that you can have high confidence in and that are robust. For example, the DRT process was very effective at finding disagreements between the production implementation for just the authorizer and the reference. We found about 25 bugs and counting. And the proofs have been very effective at finding mistakes in our design. In particular, we found 4 bugs due to failed proof attempts. So properties that we thought held about the validator in particular turned out not to hold in reality, because when we tried to carry out the proof, we failed. Okay, so now this brings us to the question of which verification language we're using. Originally, when we started building Cedar, we built all the models, so all the reference code and all the proofs in a verification system called Daphne. If you're not familiar with Daphne, it is a multi-paradigm programming language. It supports functional programming like Lean, but also imperative programming and object-oriented programming. And it has a built-in verifier that is based on reduction to SMT solving. The flavor of the verifier is horse-style reasoning. So you write annotations in your code. So you write assertions, preconditions, postconditions, and invariants. And Daphne turns these annotations into verification conditions, and it tries to discharge them automatically using Z3. This style of proof turned out to be very nice and effective for the basic properties of the Cedar authorizer. So the 3 that you see on the screen here: default deny, denied overrides allow, and sound slicing. We were basically able to get these properties almost for free. You would just write down the statement of the theorem and a couple of lines of annotation, and Z3 would just prove that this was correct. So this was really great. But we started struggling when we tried to prove the more complex meta-theoretic properties of Cedar's tools, in particular, the soundness of the validator and the soundness of the symbolic compiler. The issue with these proofs is that we were experiencing a phenomenon which is known for SMT-based tools, which is called proof brittleness. This effectively means that once your proof gets big enough, and ours got to be pretty big, the validator was about 3,000 lines of code. The symbolic compiler was even bigger. It was about 8,000 lines of code. When you get to these certain sizes and a certain level of complexity, brittleness kicks in. So brittleness means that if you change a tiny piece of the code, and we're talking syntactic changes here, like flipping 2 lines of code that are unrelated, or if you upgrade the Z3 solver, or if you upgrade Daphne, what happens is that proofs that used to verify no longer verify, okay? They completely time out. These timeouts are difficult to debug because the state of the SMT solver, which contains your proof, is opaque to you. Okay, you don't know what the solver is doing. Its state is hidden from you. So basically what you have to do is you have to look at your Daphne code and your proof, and you have to guess what facts that the solver was able to deduce previously, it's no longer able to deduce, and you have to give those facts to the solver in order for the proof to go through. This was an operational problem for us because Cedar uses these proofs to gate releases. We're not going to release a core component unless it has been modeled, verified, and differentially tested. So we had to find a way to gain control of the proofs, to get the proofs to be more stable so that we can be agile and move fast. Now, there are ways in which you can mitigate the effects of proof brittleness in an SMT-based system, but after considering our options, we decided that the most expedient way forward for Cedar is to switch to an interactive theorem prover. Our working hypothesis was that having low-level tactical control over proof construction and decidable proof checking would let us achieve the level of stability and agility that we need in order to move forward and build Cedar and make it delightful for our users and customers to use. We chose Lean because of its support for dependent type theory, which our team was familiar with, and classical reasoning, as well as the fast runtime, which was really important for us differential testing. And finally, for the extensive libraries that the Lean community has built over the years. All right. So I'm going to show you a little bit of how we did the formalization, just a tiny little flavor of what Cedar looks like in Lean, what things were easy to do, what things were hard, what kind of paper cuts we've seen. And then I'll conclude by giving a summary of the current state of the effort and what things look like in the end after we switched to Lean. So modeling the Cedar code, the algorithms in Lean was very simple. We ended up with short and beautiful and easy to read and understand code. So here's an example. This is the implementation of the authorization algorithm in Lean. This is an executable Lean function. It calculates all the policies. It runs the evaluator to find all the satisfy forbid policies, then all the satisfy permit policies. And if the forbids are empty, so nothing was satisfied, and the permits are non-empty, that is the only condition, the only path in this program that leads to allow, and otherwise the decision is denied. Okay, super short. This is 5 lines of code. The equivalent code in Rust, which is of course much more optimized and it does much more work than this, is several hundred lines of code. Okay, so the purpose of these models is to be very small, very compact, very easy to understand what's going on. The goal is not efficiency. The goal is readability and provability. Now, proving properties of this code, for those of you who know Lean, which I think is most everybody on this call, goes as you would imagine. So we basically effectively have to analyze, it's usually induction or big case analysis or induction combined with big case analysis. In this case, it's just a case analysis. And this proof here that you're seeing on the slide shows that that basic property that we talked about before, which is that forbid overrides permit, meaning if there's any forbid policy that is satisfied, then regardless of how many permits are satisfied, the answer is denied. Okay, so writing down the basic algorithms, writing down these proofs, fairly smooth, fairly easygoing. There was one tricky aspect of modeling Cedar in Lean, and this this calls back to something that I asked you to remember 20 minutes ago, which maybe you didn't. And this is how to actually represent Cedar values in Lean. Now, remember that a Cedar value can be one of 3 things. It can be a primitive, a set of values, or a record of values, which we represent as a map from string to values. You would represent this as an inductive data type, right? This is how we wrote it in Rust. This is how we wrote it in Daphne. And the natural thing was to write it this way in Lean. The problem, however, was that if you write this in Lean and you use any of the existing set implementations, either in MATLAB or in STD, the proof kernel is going to reject this. The reason is that the existing implementations use dependent types to enforce set invariants. And these proofs are effectively asking you to provide properties of the value before you define it, right? So you have to be able to show that there's an equivalence relation on these values, or there's a hashing relation on them, or there's an ordering on them. But of course, you can't do that because you're just in the middle of defining a value. You haven't defined it yet. So circularity happens and Lean rejects it. So what to do? Well, we solved this challenge by building a custom set data type and a custom map data type that is backed by a sorted dedupe list. The key here is that our custom data types don't carry proofs. okay? We do not carry and do not force those invariants in the type. Instead, we take the garbage in, garbage out approach. So if you give us well-formed inputs, we give you well-formed outputs, and we separately prove that this is the case for things that we care about. So here's an example on the slide. It shows how we create a set. We call this canonicalized procedure. Takes a input a list, canonicalizes it, sorts it, and removes duplicates. And then we prove that this procedure preserves the set elements. Another nice thing about this representation is that sets and maps do become canonical. So semantic equality coincides with structural equality, making proofs easier. Okay, so in addition to that one conceptual issue, we've also encountered a bunch of paper cuts. And I hear that some of you are working on lifting these paper cuts or on making them, smoothing out these rough edges. So thank you for that. Probably the biggest one, the one that you spent most time on was trying to integrate with Lean FFI in order to put our models into the differential testing framework. That took some sleuthing to figure out, just the usual problem, sparse documentation and examples. We would have wished for termination checking for mutual induction to be faster. Cedar has a lot of mutually recursive things in it, and those proofs tended to be sluggish, and we basically had to come up with tricks to avoid using mutual induction when that would have been a natural way to do it, and just use plain induction. So those are a couple of examples. Some things that we really wish for Lean is for it to support the full range of signed and unsigned finite integer types, things that you would find in Rust. And for better automatic derivation of equality and ordering. So for example, for that value type that you've seen before, Lean cannot derive the equality on that type automatically. So you have to write a lot of grungy code that basically does automatic derivation over those deeply nested types that combine lists and sets and maps with values, or also Cedar expressions. Okay, overall though, we were able to complete the switch in a couple of months, and it was a big operational win for us. Our verification time is now about a third of what it was in Daphne, and the differential testing is about 3 orders of magnitude faster. We were able to make the models of Cedar in Lean much shorter and more concise, thanks to the features of Lean, such as type classes, being able to define your own custom notation, being able to reuse the libraries in Lean and freely use higher order functions and be able to do proofs with them, thanks to the many, many theorems that exist about them. We did pay a price in added proof overhead, but it wasn't that high. The proofs in Lean ended up being only about 60% bigger than the corresponding proofs in Daphne. Most importantly, we gained productivity and maintainability. So to give you an example, I did this validator proof in 18 workdays. This proof was around 3,000 lines in Daphne originally. It ended up being about 4,600 lines of code in Lean. Now, the thing that's interesting about this story is that the validator took much longer to develop originally. It was developed by 2 people over a longer period of time. That's not an apples-to-apples comparison, so you shouldn't infer much from this, except for the following fact, that once the 2 people who originally did this proof figure out the hard parts, for example, the right definitions to use and the right inductive invariants, so we knew that the proof was possible and I was able to reuse those. Actually, mechanizing that proof in Lean is a simple, efficient engineering activity, similar to how you can code up an algorithm, a tricky algorithm that you worked out on paper. You can code it up directly and quickly in a programming language. So that's what the experience was for me, rebuilding this validator proof in Lean. You also don't have to be a Lean expert to do this. I am by no means a Lean expert. This validator proof is only the second substantial proof that I've done in Lean, the first one being a few years ago in Lean 3. Another really important thing that we have gained by switching to Lean, in addition to added productivity and speed, is maintainability. it turns out that the lean proofs are fairly stable even to and robust to even to invasive changes to deformalization. For example, recently we switched out MATLib, completely ripped it out of our formalization and replaced it with a smaller and leaner standard lib in just a couple of hours. Proofs break, of course they do, if you change definitions or you change tactics and so on. But these breaks are small and they're highly localized. You can just drop into the tactic state, see what broke, and fix it. So that's all I have. Thank you very much for your attention, and I will be happy to take any questions now.
Thank you very much, Emina. I'd like to request that everybody who wants to ask a question raise their hand using the Zoom feature. All right, first up is Wojciech.
Hello, thank you for the presentation. So presumably the reason for having a separate reference and separate production implementation is speed. And if the reference one was as fast as the production one, you could just, have a single implementation and do away with DRT completely. So I'm wondering, have you benchmarked the Daphne and the Lean implementations and compared them? Like how much slower are they relative to the Rust implementation?
So that's a good question and a good point. Speed is definitely one of the concerns, but the other concerns which are perhaps even more important than speed are the operational concerns, meaning the being able giving other people ability to easily integrate with your APIs. So Rust is a commonly used programming language, and it gives us speed, and we also spend a lot of time thinking about Rust APIs, and it's very easy to integrate with Rust, not only with Rust directly, but also from other programming languages with Rust to language bindings. So we did do a bit of, I don't want to call it benchmarking, but we did testing, which is what I've seen on this previous slide. And for these small randomly generated test cases, which are not testing performance, by the way, they're not big enough. They're really there to test coverage. Lean is actually quite fast. It is on the same order of magnitude as Rust, as you can see. But yeah, our main concerns are speed and perhaps more importantly, these software engineering operational concerns, how you integrate with this production engine that we provide to you.
Patrick?
Thank you very much for this presentation. I found it very interesting, and I'm a pure mathematician. I have no idea about what the real world looks like, and it's really nice to see this tool being used in industry. And I've got a couple of naive questions. So first about the size of policy. So how do you end up with hundreds of thousands of rules? Is it because like each resource has its own rule, and this is what makes it bigger? Or,
it depends. There are different ways in which people model access. So you can write what we call static policies, which are really talking only about groups, and they're quite abstract. They give access based on properties. But for a lot of applications, when you're giving ad hoc access, you basically just want to fix the tuple. You want to say things like, Emina is allowed to read this cat.jpg file. And for those kinds of things, and for applications where it makes sense for this access to be quite concrete, you're going to end up with a lot of policies. So imagine having a huge online photo sharing store, and each user is allowed to give access to other users personally, right, on their own resources. So you're going to end up with a policy stores with like hundreds of thousands of policies. So it really depends on the granularity at which you're giving access.
Okay, thanks. That's what I thought. So I've got another question about young people in the community. I'm very safe playing with Lean as a mathematician because I'm a professor and I've got my lifetime job. But we have many young people who are enthusiastic about mathematics and formalization, and we need to think a bit about what could they do if they don't find an academic job. Don't find a professor position. And I would like to know, do you have any advice to give to those people if they want to have the option of using their formal method skills in industry if they don't go to academia, something they should do or learn in anything really?
Yeah, I mean, it's a great question. So there are, I can't answer for mathematicians, so let me answer for computer scientists. There are quite a few companies, including Amazon, where people do use formal methods heavily, and they will use things like lean and so on and so forth. It doesn't even have to be big companies. There are also small companies that do this. So really, the key is looking for opportunities like that, looking for companies with a track record of using formal methods to build things. If you're in the US, there are also lots of companies that do work for the government, and those companies also will use formal methods heavily. In general, though, what I found is even if a place doesn't use formal methods to begin with, you can convince the leadership in your company. I've done it a couple of times in other places to do so by showing value. So in industry, people really care about writing good code, writing stable code, writing correct code, and people understand the limitations of testing and they're open-minded. But really, what you need to be able to do is identify pieces of the infrastructure that you're building that are critical, where the additional effort and time that you have to put in to prove it correct is worth it. And almost everywhere, there is a place to do that. And once you do it and you roll your sleeves up and, you know, maybe you do it as a side project before you tell your boss. Once you demonstrate the value, I have found, at least in my experience, that people are extremely receptive to formal methods once you found the right niche, right? Like the right place where this extra investment and extra time is worth it. You get the benefit that you need.
Thanks.
Mac?
So I was a bit curious. You mentioned that one of the problems you encountered was related to FI code and interactions there. I'd be curious as to what particular, like, a bit more details on what kind of paper cuts you encountered in that regard and what you would like to see improve there.
So I will defer that question to one of my teammates who has done the integration with Rust. I was not the person to do that. I mostly worked on the proof and the front end. So if you email me after the talk, I will put you in touch with Kesha, and she can answer these questions. But from what I understand, it was mostly finding examples of how to integrate with FFI. And for us, the issue was also that we were doing it from Rust, not from C. So that was another problem. And we suspect that there might be a memory leak somewhere in the FFI, which again is one of those things that is hard to diagnose and debug. And right now we're solving it by just increasing the memory that we use during differential testing. But all of those simple things, all those small little things it would be super helpful to talk to someone who's worked on the FFI and see if we can solve them.
Makes sense?
Shira?
Yeah, at some point you mentioned that in order to ensure constant time lookups.
Sorry, can you turn your microphone up? I can't hear you.
Is this better?
Um,
Is this better?
Yes.
Okay. So at some point you mentioned that in order to ensure constant time lookups, you store the transitive closure of your DAG instead of just the DAG itself, so that you don't have to actually do the computation. And I guess in practice, the space considerations are just negligible, or the trade-off is significant enough to be worthwhile, or
Yeah.
is there any concern about the space considerations?
No. So at the scale at which we operate at Amazon, you know, the motto is storage is cheap. So we will often trade space for time whenever we can.
Yeah. Okay. Thanks.
Thomas?
Yes, thank you. When you said that there were 25 discrepancies between the sort of specification and the production implementation, were those issues in the production implementation How many were issues on each side?
That's a good question. I think we have that data somewhere, but I can't recall it off the top of my head. Most of them were in the production, and the reason is simply that there's much more code there. It's doing much more complicated things versus the reference. Some were, back when we were in Daphne at least, discrepancies between, for example, how Rust handles strings and how Daphne handles strings. So this would also be something that differential testing would find. But those were the sort of bugs that we were finding.
Thank you.
David?
Hi. You mentioned that like one pattern that you've used that Cedar shows up in it is like users sharing access to documents to other users. And I'm just curious, like, what that looks like when you model it. And in particular, does like because that's like modifying the set of facts that Cedar is reasoning over. So like, is there like self-reference there? Can Cedar express like Alice is only allowed to grant access to Alice's own documents?
The use case that you have in mind. So Cedar is a pure function. So for every authorization function, for every authorization call, you give it the set of policies that are relevant. It is up to the application or or a service, if we're talking about a service that's using a Cedar, to select those policies. Usually what happens, the way that people implement the scenario that you're talking about is that you have a user-facing UI where the user, for example, gives access directly to a photo to somebody. This UI translates this click into an instantiation of a Cedar template, which represents a family of policies. So templates is not something that we talked about in this talk, but effectively that's how it works. So the template gets added to the policy store. And then when the authorization request comes in, the authorization service will pull up the instantiation of that template if it is relevant in order for to answer a specific authorization request. So there is state, but the state is outside of Cedar. So the thing that we model, that we care about, that we prove is the stateless part where after the fact, after the policies have been selected and the relevant part of the hierarchy has been pulled in, we evaluate to tell whether access is allowed or not.
Okay, thank you.
Does anybody else want to put their hands up? Great. I have time for mine then. Did you use an off-the-shelf differential testing framework or did you roll your own?
We used the Rust built-in one, libfuzzer.
Cool. Thanks.
Oh, CargoFuzz, sorry.
Yeah.
CargoFuzz.
Alex? You are inaudible, Alex. In just a moment. Okay. It seems that Alex is having technical difficulties. Would anybody else like to ask a question in the meantime? Lars?
Yeah, given the size, with millions of entities, you said, of your DAG, is the system handling this completely synchronous, or is there asynchronous communication in there? And if there is, for example, I think garbage, you're removing something might be very expensive. So how was your experience with proving distributed or computations or asynchronous computations with something like Lean?
So that is not a part that Cedar itself handled. This is something that the application of Cedar would handle. And it is not something that we have modeled yet, but you're right. That would be a super interesting thing to model, actually, to model a service that manages the entity graph and that manages the policy store, and it has to use distributed algorithms to do this, because as you know, this process has to be asynchronous, and to see what kind of consistency properties we could prove about it in Lean. So that is definitely a super interesting thing to do in the future.
So I just asked if Alex wanted to send me a written version, and I think that my computer just said that it popped in. If I could
Not, he
actually.
sent it to me, so
Ah.
I can read his question.
Oh, great, thanks.
So Alex is asking, when you talk about finite signed integers, do you mean types with a specific number of bits, like 8, 16, 32, etc.? So this is something that they're working on with the bitvec type. And Alex would be curious to hear if there are any specific or unusual things that you'd need from this type, I guess, beyond the standard.
So I'm already using the bitvec type. Thank you for developing it inside of the model for the symbolic compiler. But I was thinking more along the lines that it would have been in some places convenient to have something that looks like, in Lean we have uint64, uint32. So if you had assigned versions of that, the same kind of integer types that you would find in a language like Rust. So that would make our modeling easier because, of course, eventually we write all of this code in Rust.
And that's all the time that we have for questions. I'm sorry, Robert, your question will not get asked.
I was just going to read Alex's. So.
Okay, great. So, Emina, thank you very much for this really great talk. I don't know, I think that you're too busy to be attending the rest of the conference. So I'd encourage people to send email questions if necessary. Given that you already invited that earlier, I think it's okay. It's fair to say so.
Yeah, please do, please do. You can also join the Cedar Slack channel. So there you can reach not only me, but the entire team. We're a super friendly bunch, and we're super fast at answering questions. So if you join this Cedar public Slack channel, we'd be happy to engage.
That's wonderful. Thank you very, very much.
Thank you so much.